All right, this lesson is all about how computers store numbers. Now, there are a lot of details in here that might at first seem weird to you, and my best advice for this topic is to really just pause the video, work through examples, make sure you understand every single little step that's done, and it will become more comfortable and less strange to you the more you practice. So, the way computers store numbers is based on a standard of the IEEE, that stands for the Institute of Electrical and Electronics Engineers, which is, I think, the world's largest technical organization. And so most computers, maybe all computers, are built on this standard. And I'm going to walk you through how numbers are stored in steps. So the first step is to just think about what we'll call a normalized number. And a normalized number has the form plus or minus, so we say if it's positive or negative, then 1 point, and then a kind of part of the number that comes after the decimal that's called the mantissa, and it's going to be in binary, and then times 2 to an exponent. Okay, so here's a quick example of how we think about this. Take the base 10 number, 23.171875. If you were to convert that to a base 2 number, it would be written 10111.001011. Okay? And so in normalized form, that would be a plus, because it's a positive number, and then a 1 dot, and then all of these numbers here, that's the mantissa. And then this number here, the 4 and the 2 to the 4th, that's the exponent, okay? This leading one right here, we never store that, okay? And the reason you never store it is that it's implied. It's like a built-in part of the number that's always there. There are different levels of precision that a computer might use to store numbers. So there's something called single precision, where the exponent has 8 binary digits and the mantissa has 23. There's double precision, where the exponent has 11 and the mantissa has 52, and then there's this thing called long double. We're almost always going to be using double, maybe exclusively. That's what we'll be thinking of. And so, again, the way to think about double precision IEEE standard floating point representation is that there's one bit, one binary digit that represents the sign, positive or negative. So 0 means positive and 1 means negative. And then the exponent is made up of 11 bits, so 11 binary digits. And then the mantissa is made up of 52 bits. And of course, don't forget there's that 1 dot part that goes before the mantissa, but we don't store that. That's implied. So let's go back to this example from before. We had the number 23.171875. The sign is 0 because it's a positive number, and then the mantissa is all this stuff here. So there's the things I've underlined, right, which appear here, and then the rest we fill in all with zeros because we go out to 52 places. And in case it helps you see that long mantissa better, here it is separated into 4-bit chunks. Let's talk about the exponent for a minute. The exponent is made up of 11 bits, right? So that's like 11 spaces, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And each one can be a 0 or a 1. So that's 2 to the 11th, or 2048 different integers that it can represent. Now, we don't only want to represent large numbers with our floating point representation. We want to have both positive and negative exponents, okay? So of these 2048 different integers that we can represent, 2 we're going to save, okay? And I'll tell you what we're saving them for later. And that leaves 2046 left over. And we want to be as unbiased as possible, okay? So we're going to let these 2046 integers that we have actually represent negative 1022 to positive 1023. And if you add those two numbers, ignoring the minus sign, you get 2045, but of course there's 0, is the 2046th. So this range is 2046 integers. And so there's this thing called the exponential bias, okay? And what that is the number that you add to the actual exponent to store, okay? So in other words, if you wanted to store the exponent minus 1022, what you would do is you would add 1023 to it, that equals 1, and then the exponent that you would store is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. That's an 11-bit exponent that represents the number 1, but you can go backwards. If you see this exponent, you subtract that bias of 1023, and you get minus 1022. Okay, so again, here as an example, this number in normalized form, the plus turns into the 0. This stuff here, this stuff turns into the mantissa over here, those 52 bits. And then there's this 2 to the 4th. And since 4 plus the bias 1023 is 1027, then that's what these 11 bits represent. This is the binary representation of 1027. This one is in the 1024's place. This is plus 2, and this is plus 1, so that's 1027. And again, the reason for this exponential bias is that we want to have a way of representing positive and negative exponents without having to keep track of another sign, and this is the way that it's done. Okay, so I told you that of the 2048 integers we could represent in the exponent, 2 of them we were saving for special cases. We're not going to obsess about these, but this is just so you know what they are. If the exponent is 2047, then it's equal to infinity. The number is set to represent infinity if the mantissa is all zeros. If the mantissa is not all zeros, but the exponent is 2047, then it represents this thing called not a number. Okay, then the other choice is if the exponent is 0. That's the other exponent that's saved. These are used to represent numbers called subnormal numbers, which are very small. They're mentioned in the book. We're not going to worry about these here. Okay, so you can do a few more examples if you want. We could take this binary number, and in floating point form, this would have 1 as the sign because it's negative. And then it would have the mantissa needs to capture these digits here. So that's why you see 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1. That's these digits. Okay, and then you have to count how far over we have to shift those, and we have to shift it over 1, 2, 3, 4, 5 decimal places. Okay, so that's going to be times 2 to the 5th. So if you want to have an exponent of 5, you have to worry about that exponential bias. So we want to represent the number 1028. And that's what you have here. This is in the 1024's place. This is in the 4's place. So these 11 digits represent 1028. Okay, so you should do the practice. You can pause this video and just see what these numbers here represent in binary. It's worth doing the exercise. So it may be that you have a number which, when you try to put it in the format we've been discussing, requires more than 52 bits in the mantissa. And so there's various ways you can approximate, right, to get down to just 52 bits in the mantissa. One is called chopping, which means you ignore all the digits after bit 52, but that's not what's done because that systematically rounds things downwards, right? And this can result in undesirable computational consequences. So instead we use something called rounding, and in particular something called nearest neighbor rounding. So what you do is you put the number in this form, and if what's left after the 52 bits in the mantissa starts with a 0, then you drop them. If it starts with a 1, like here, then what you do is you get rid of all that stuff, but you add 1 to the bit in position 52, and of course that may cause you to have to carry other bits over, about carrying when you do addition. So that's a thing that can happen. And then, of course, there's a special case where you have something that's a 1 followed by all zeros, and that's all following the 50-second bit. And that's exactly the borderline between the two previous cases. And this is going to seem really weird, but what you do in this case is that if the 50-second bit is 1, then you take this one and you add it here. And if the 50-second bit is 0, then you do nothing, right? You just chop it off so that you're basically rounding down. And it turns out those two cases are equally likely to happen. So this is a way of a computer trying to like make errors that will hopefully cancel each other out while you're doing lots of calculations. There's an important number called machine epsilon, and we write it this way or this way. And what it represents is the distance between the number 1 and the next smallest number that your computer can represent. Okay? So in IEEE double precision representation, that next smallest number is 1 plus 51 zeros followed by a 1. So that's 1 plus 2 to the minus 52nd power. And the difference between that number and 1 is just this bit here. So this machine epsilon is 2 to the minus 52nd power, and if you just try to translate that, you can do it approximately or exactly with a calculator. It's equal to about 10 to the minus 16th, okay? And if you type dot machine $double.eps just at the prompt in R, then you'll see what machine epsilon on your machine is. A good exercise for you to do would be to repeat this, but instead of starting with the number 1, see what the distance is between 2 to the 20th and the next smallest number that you can represent in IEEE double precision. And so the first thing you need to do is just take 2 to the 20th and write that in the standard format, and then see what's the smallest thing you can add on. So let's talk more about rounding. When you round numbers on a computer using this floating point representation, right, you're changing your actual intended number, and we have to be able to figure out what the error is in that. So to make a concrete example, let's take the base 10 number 9.4, which in binary is 1001.0110 repeating infinitely. So the 4/10 in the 9.4 translates into this business here. And if you put this in floating point format, you get a plus and a 1 dot, and then a 0010. That's these 4 bits here. And then you have to worry about the repeating stuff. So you get 110, and then you go back to the start of your repeating part, 0. So that's where this 1100 comes from, and then it repeats over and over again. But when you do your rounding at the 52nd bit, because the repeating part starts with a 1, what's going to happen is the trailing 0 that you've seen in the repeating part gets rounded up to a 1 here in the 52nd bit. So what did we actually do? We truncated the tail by this 1100 infinitely repeating pattern starting out after the 52nd bit, right? Except that the whole thing was multiplied by 2 to the 3rd, right? That was the exponential term here. So in short, you truncate, when you did the rounding process, you threw away all this repeating stuff, which if you calculate it out, turns out to be 0.8 times 2 to the minus 49th power. But then you didn't just truncate, you added, because you turned the 0 that was supposed to be here into a 1 due to rounding. So what you did there was you added 1 in the 2 to the minus 52nd place, but the overall exponent was 2 to the 3rd. So what you did was you added 1 times 2 to the minus 49th power. And so you can compute a negative sign on this stuff, right, that you threw away, and you can compute a plus sign on this stuff, and if you calculate that out, the 1 minus the 0.8 gives you a 0.2 times 2 to the minus 49th. So the floating point representation of 9.4 is actually 9.4 plus 0.2 times 2 to the minus 49th power. We can talk about the absolute error as just the magnitude of the difference between the actual number and the floating point representation. So that's this bit here. That's 0.2 times 2 to the minus 49th. And we can talk about the relative rounding error, which is just the absolute error divided by the true number. So it's like what fraction of the true number is the error. And here that turns out to be 8/47 times 2 to the minus 52nd. We won't show this, but it's not too bad to show that this relative rounding error is always less than or equal to machine epsilon divided by 2. I'll just say a few words without doing the details. We're not going to do them, but we'll say a few words about the addition and subtraction of floating point numbers. There is a register or a part of your computer that's dedicated to doing computations so that addition itself can be done with higher precision. So what you do is you take your numbers that you want to add and you kind of line up the decimals and you do the addition and subtraction. And for now, you can imagine that when you're doing that addition and subtraction, you don't have to worry about rounding yet. But then once the arithmetic is complete, then you have to round it back into floating point form. We're not going to delve too deeply into that, but in case you were wondering. All right, thanks for listening.